useful when you're solving problems involving circuits or working with circuits in general are what are called Kirchoff's rules. Kirchhoff has two rules, and they both follow from basic conservation laws. The first rule is the junction rule, which says that the sum of the currents entering a given junction must be 0. Or another way of saying it would be that the current going into the junction flows or goes out of the junction. Okay, let me show you what I mean by this. So we've got a circuit. We'll just make a simple parallel circuit here. Okay, so a junction is a point where any two wires connect. For example, right here, this would be a junction in our circuit. Any current, there's some current flowing this way, we'll call that I, and then that current splits between here and here. Call this I2, call this I3. At this junction, there can't be more current going into the junction than comes out of the junction. Otherwise, that would either violate conservation of charge, or we just have charge building up at this point, which doesn't make a lot of sense. So that's what the junction rule is. The junction rule says that this current going into the junction is equal to the current coming out of the junction. It goes out in two directions, so this total current is equal to current 2 plus current 3. Or another way of saying it is that you could say that going into the junction is positive and going out of the junction is negative, and that this total must be equal to 0. This could be more useful for solving the systems of equations that you're going to have to deal with as you apply Kirchoff's rules. All right, Kirchoff's second rule is called the loop rule. And the loop rule comes from conservation of energy. The junction rule is related to conservation of charge. As I said, that same amount of charge has to go into the junction as goes out, otherwise there would be charge being created or destroyed. The loop rule has to do with conservation of energy. The loop rule says that the voltage drop around a closed loop is 0. So meaning that any closed loop, if we look at the same circuit, if we pick any loop, meaning a circle kind of starting, well, it doesn't have to be a circle, but starting and ending at the same point. So if I go around this loop, as I go around, the total voltage drop must be 0. So we have some EMF across the battery, then we have some voltage drop across that resistor. I'll call this R3. So we have a voltage drop across the resistor, and then we're back to where we started. That must be equal to 0. You could take another loop. Say we take this one. Now over here, we know that current is going to be flowing downward. So as we go this way, I would call that a positive change in voltage. Whoops. This is R2. Okay. So we call this negative a voltage drop going this way. So I'll call it a voltage increase going the opposite direction. In general, for these, you just assume that current is flowing in one direction, and you apply the appropriate signs. If it turns out you're wrong and current is flowing the other direction, you'll just get a negative number for the current, and it'll be fine. But anyway, so we've got a voltage increase across this one, then we figure we probably got a voltage drop across that one, so that would be how we get the loop rule for this one. We could also do the outer loop all the way around the outside, and in that case we have the EMF of the battery, and then wire, wire, wire. Okay, then we have a voltage drop across that resistor too, and then we're back at the other side of the battery. So these are three equations that can come from the loop rule. Now notice that there are multiple different equations we can get. We can use the loop rule, we can use the junction rule. In general, you'll work these through and get a system of equations that you'll then have to solve. I said the loop rule comes from conservation of energy, which it does. For reasons that are probably obvious, the potential difference between this point and itself is 0. The potential at a given point can't be two different values. That doesn't make any sense, because that would mean that going from this point to this point, going from this point to this point, the same point, you could gain energy somehow. That'd be like if you're, say you're standing on the ground and you walk up a hill and then you walk down the other side of the hill back to the same level, and now you suddenly have a different amount of gravitational potential energy. That doesn't make any sense. It would violate the conservation of energy. So if the potential difference at this point wasn't equal to the potential difference at this point, then as you go around the loop, you'd either be continuously gaining energy or continuously losing energy, either of which would violate the conservation of energy. So even if I go around a loop, the potential at this point and has to be the same as the potential at this point still. So since the potential at this point is a single value, you can't have two different potentials at the same point. Then if you start at this point, end at this point, then the total potential difference must be 0. So those are Kirchoff's rules: junction rule, loop rule. 2 rules get you a lot of equations that you can then put into a system of equations and use the matrix capabilities of your calculator to solve.